He then explains to her what's going on. First, you could have said that in the first place and say numerous lies. Second, that's complete bullshit. He was only given an accurate. Listen, I'm sure you've just started here and don't really know how it goes, right? Never a name. But whatever, remember, Pete, you'll never guess where he stays. Apparently, it's the only hotel in all of Berlin. And because everyone's just killing everyone for no reason, he executes the receptionist. Then he goes upstairs to the bathroom because he checked in his cigar for reasons that still make no sense. And I swear to God, everyone in this movie is so bad at what they do. This guy didn't even recognize until this guy tries to kill him, has two guns pointed at him, and even stops to quote Dirty Harry. Feeling lucky? This guy just stands there through all of that instead of pulling either of the triggers. And this dumb bitch gave him a single bed when he clearly asked for a double.
And would you prefer 2 single beds or 1 double?
1 double should be plenty, dear.
So, Pete gets shot 3 times with a shotgun, then falls head first from the 2nd story. We've definitely seen the last of him. Now,
room illuminates.
Oh no,
perceptible
they
delay.
muted you for no
You
reason.
make a phone
I'm
call to
sorry about
someone
that,
on
my
the other side
friend.
of the planet,
I'm
and
sorry
their
about
voice
that.
arrives as if they
So
had
sad
sat
story.
next to you. Light dominates human experience so completely that most people never consider the possibility that it has a finite speed at all. It feels limitless. It feels infinite. It is not infinite. And recognizing that it has a limit was only the beginning. Because recognizing that it has a limit also meant
So
recognizing
sad story.
that its limit is absolute.
Sorry about that, my friend.
Not merely very large. Not merely practically unreachable. Absolute in the way that the laws of mathematics are absolute. Woven into the fabric of reality at a depth that no amount of technological progress can ever touch.
I'm sorry about that,
The
my
journey
friend.
toward this devastating
I'm sorry, I'm so
realization
sorry.
began with an experiment designed to measure something.
I hope you're not upset.
The first cracks in human intuition about light appeared in 1887, when two American physicists named Albert Michelson and Edward Morley designed an experiment that everyone expected to be straightforward. Their goal was simple.
Yes?
Measure how the Earth's motion through space
Oh, I see.
affects the observed speed
Ah,
of
because of
light.
Koos.
The reasoning behind the
Yes,
experiment
I think so.
is completely airtight.
Mm.
If you are standing on a moving train and you throw a ball forward, the ball's speed relative to the ground equals the ball's speed relative to you plus the train speed. This is basic addition. Every physicist in the world expected light to follow the same principle.
But it doesn't.
Earth orbits the sun at approximately 67,000 miles per hour.
Red shifts, but
That means
they
the
still
Earth
say
is
the same
hurtling through
speed.
space at tremendous velocity.
that's weird.
A beam of light emitted in the direction of Earth's motion should travel slightly faster relative to a stationary point.
It
than a
doesn't.
beam
It just
emitted
gets more
in the opposite
compressed.
direction. The difference would be minuscule relative to the speed of light itself, but Michelson had built the most sensitive optical instrument ever constructed. His interferometer could detect changes in light speed far smaller than what Earth's orbital velocity should produce. The experiment was meticulous. The equipment was precise. The prediction was clear. The result was zero. Absolute zero. No difference. The speed of light came back identical in every direction, regardless of how the Earth was moving. It did not matter which way the light was aimed relative to the Earth's orbit. It did not matter what time of year the measurement was taken, when Earth's velocity pointed in completely different directions through space. The speed of light was fixed, constant, immovable.
But then the
The
redshift.
result confounded physicists for nearly 20 years. It violated everything common sense dictated about how motion and speed should interact. Research teams across Europe and America repeated the experiment with increasingly refined instruments. They tried different altitudes, different orientations, different seasons. Nobody could make the speed of light change. It sat there, stubbornly identical under every conceivable condition, as though the universe was insisting on something that human intuition refused to accept. In 1905, a 26-year-old Peyton Clark working in Bern, Switzerland, published a paper that
Einstein.
explained everything. His name was Albert Einstein,
Because of Koos.
and his paper introduced the special theory of relativity. The core of the theory rested on two postulates that appeared almost trivially simple when stated in plain language. First, the laws of physics are identical for all observers moving at constant velocity relative to one another. Second, the speed of light in a vacuum is the same for all observers, regardless of how those observers are moving or how the light source itself is moving. Two statements. They sound calm, almost boring, almost like something everyone should already agree with. But when Einstein followed the mathematical consequences of those two postulates to their logical conclusions, the universe transformed. The reality that emerged from the math was so alien, so counterintuitive, so violently at odds with everyday human experience, that more than a century later, most people still have not fully absorbed what it means. Here is the first consequence. If the speed of light is truly the same for all observers, then something else must adjust to compensate. Something must give. The thing that gives is time. Consider two observers. One stands motionless on a platform. The other flies past on a spacecraft at 50% of the speed of light. Both observers watch a beam of light bouncing between two mirrors mounted vertically inside the spacecraft. The observer on board sees the light traveling straight up and down in a simple vertical path between the two mirrors. The observer on the platform sees something profoundly different. From the platform, the spacecraft is moving sideways at tremendous speed. The light beam still bounces between the two mirrors, but because the mirrors are moving laterally while the light is in transit, the beam must follow a longer diagonal path to get from one mirror to the other. Both observers must measure the same speed of light. That is the rule the universe enforces without exception. But the platform observer sees the light covering a longer diagonal distance. If the speed is identical and the distance is greater, then the time between bounces must be longer as seen from the platform. Time aboard the spacecraft runs slower than time on the platform. This is not an optical illusion. It is not a trick caused by signal delays or processing errors in the brain. Time itself, the actual physical progression of moments, literally passes at a reduced rate for the moving observer. This phenomenon is called time dilation, and before anyone dismisses it as theoretical abstraction, know this. Time dilation has been directly measured using atomic clocks flown on high-speed aircraft. In 1971, physicists Joseph Hafele and Richard Keating placed cesium beam atomic clocks on commercial airliners and flew them around the world, eastward and westward. When the airborne clocks were compared to reference clocks that remained on the ground, the differences matched Einstein's predictions within experimental error. Decades later, the effect was measured with even greater precision in particle accelerators, where unstable subatomic particles called muons survive measurably longer when moving at near light speeds than when sitting still. A muon at rest decays in about 2.2 microseconds. A muon traveling at 99.9% of light speed survives for roughly 50 microseconds, as measured by a stationary lab clock. The particle does not become more durable. Its internal clock simply runs slower. Time dilation is also corrected for every single day in the GPS satellite constellation orbiting the Earth. Each GPS satellite carries an onboard atomic clock and orbits at approximately 14,000 kilometers per hour. Without relativistic adjustments accounting for the time dilation experienced by those satellites, along with a counteracting general relativistic effect from weaker gravity at orbital altitude, your GPS position would drift by approximately 6 miles every single day, accumulating, compounding, making navigation useless within a week. Relativity is not abstract philosophy. It is operational engineering that billions of people unknowingly depend on every time they open a maps application on their phone. The second consequence of Einstein's postulates is equally disturbing. If time changes for moving observers, space changes too. An object moving at a significant fraction of the speed of light appears physically compressed in the direction of its motion when measured by a stationary observer. This is called length contraction. A spacecraft traveling at 86% of light speed would appear to be squashed to exactly half its resting length as measured by someone watching it fly past. The crew on board would notice nothing unusual inside their ship. Their measuring instruments contract by the same proportion. Their bodies contract. The walls of the ship contract. Everything shrinks together in perfect lockstep, making the compression completely undetectable from inside the moving reference frame. But from outside, the compression is physically real and experimentally measurable. These twin effects reveal something that fundamentally overturns the way human beings have always understood reality. Space and time are not separate, independent stages on which the events of the universe play out. They are two interwoven aspects of a single unified fabric that physicists call space-time. Motion through one dimension of space-time directly and inescapably affects the other. The faster you travel through space, the slower you travel through time. This is not a poetic analogy. It is the tested, measured, confirmed, and technologically exploited behavior of the physical universe we inhabit. Now we arrive at the point where the dream of starflight begins its long, irreversible collapse. Buried inside Einstein's equations is a mathematical term that shows up in every single relativistic calculation. It governs how time dilates. It governs how space contracts. It determines how momentum changes at high velocity. And most devastatingly, it controls how the energy required to accelerate an object scales as that object moves faster and faster. This term is called the Lorentz factor, named after the Dutch physicist Hendrik Lorentz, who first derived it. The Lorentz factor is computed by taking 1 and dividing it by the square root of 1 minus the square of the object's velocity, divided by the square of the speed of light. At the sluggish velocities humans encounter in daily life, the Lorentz factor is indistinguishable from 1. A car on a highway, a jet aircraft at full throttle, even the space station orbiting Earth at 17,500 miles per hour, all experience a Lorentz factor, so trivially close to 1 that its effects are invisible without extremely sensitive instruments. A clock on the International Space Station gains roughly 0.01 seconds per year over a clock on the ground, undetectable to human senses, irrelevant to engineering, essentially 0. But the Lorentz factor does not stay near 1. As velocity climbs toward a meaningful fraction of the speed of light, the factor begins to grow. And the manner in which it grows is the key to understanding everything that follows. At 10% of the speed of light, the Lorentz factor reaches approximately 1.005, a rounding error. At 50% of light speed, it climbs to about 1.15. Time passes roughly 15% slower for the moving object compared to a stationary observer. At 90% of light speed, the factor jumps to approximately 2.29. Time for the traveler now passes at less than half the rate experienced by the observer left behind. Significant, dramatic even, but manageable in the imagination. Now watch what happens near the boundary. At 99% of light speed, the Lorentz factor reaches approximately 7.09. At 99.9%, it leaps to about 22.4. At 99.99%, it soars above 70. At 99.999%, it blows past 220. Each additional 9 after the decimal adds not a small increment, but a massive multiplicative jump. The curve bends upward like a wall rising from flat ground, slowly at first, then steeply, then nearly vertically. The progression has a relentless, suffocating quality. Going from 90% to 99% of light speed triples the Lorentz factor. Going from 99 to 99.9% triples it again. Each step closer to the limit demands roughly the same multiplicative increase in the factor, and as we are about to see, the same multiplicative increase in energy cost. The numbers do not plateau. They do not level off. They do not approach a ceiling. They accelerate upward with a ferocity that makes exponential growth look gentle by comparison. And at the speed of light exactly, the equation produces a division by 0. The Lorentz factor does not reach a very large number and stop. It does not plateau at some extreme but finite value. It becomes undefined, infinite, mathematically meaningless. The equations of space-time simply refuse to produce a result at that velocity for any object that possesses mass. This is the wall. This is the barrier that no technology, no material, no fuel, no amount of ingenuity can overcome. It is not a wall that stands in the path of a traveler the way a mountain stands in the path of a hiker. It is a wall woven into the geometry of the path itself. You cannot reach the speed of light because the mathematical framework describing motion ceases to function at that value. The analogy that comes closest is trying to travel north from the North Pole. There is no physical barrier at the North Pole, no fence, no wall, no sign saying you cannot continue. But north does not exist as a direction beyond that point. You can stand at the pole and point in any direction, and every direction is south. The concept of further north has no meaning. The speed of light occupies the same structural role in the geometry of space-time. Faster is not a direction available to objects with mass once the light speed boundary is reached. The concept itself evaporates from the mathematics. The distinction between an engineering barrier and a structural impossibility is the single most critical concept in this entire story, and confusing the two is the source of nearly all false optimism about interstellar travel. Engineering barriers yield to better engineering. The sound barrier terrified aviators for years. Aircraft approaching the speed of sound encountered violent turbulence, lost control authority, and sometimes disintegrated. Many engineers believed supersonic flight was physically impossible. Then in 1947, Chuck Yeager climbed into the Bell Zone and broke through. The barrier was real, but it was aerodynamic. It arose from the interaction between an aircraft structure and the behavior of air molecules at high compression. The speed of sound is determined by molecular properties of the atmosphere. It changes with temperature, it changes with altitude, it changes with the composition of the gas. There is absolutely nothing fundamental about it. It does not appear in the deep equations of physics. It has no special status in the architecture of reality. The speed of light is categorically, qualitatively, structurally different. The speed of light appears in Maxwell's equations, which govern all electromagnetic phenomena. It appears in Einstein's field equations, which describe the curvature of space-time caused by mass and energy. It connects the dimensions of space to the dimension of time. It connects mass to energy through the most famous equation ever written. It sets the maximum rate at which any causal influence can propagate between 2 points anywhere in the observable universe. The speed of light is not a property of light. It is a property of space-time itself. Photons travel at that speed because they have zero mass. The speed was already there, embedded in the structure of reality, before any photon ever existed. Breaking the sound barrier required building a faster airplane. Breaking the light speed barrier would require rebuilding the laws of physics from the ground up, and those laws are not ours to rewrite. There is one more subtlety that popular explanations of relativity almost always skip, and leaving it out creates a dangerous illusion of loopholes. At everyday velocities, speeds combine through simple addition. If you walk at 3 miles per hour on a train, traveling at 60 miles per hour, a bystander on the platform sees you moving at 63 miles per hour. Obvious, intuitive. But this arithmetic rule quietly disintegrates at relativistic speeds. Einstein's equations show that velocities do not add linearly when they constitute a meaningful fraction of the speed of light. Instead, they combine through a relativistic velocity addition formula that always, without exception, produces a result less than the speed of light. If a spacecraft travels at 90% of light speed relative to Earth and launches a probe forward at 90% of light speed relative to the ship, a stationary observer on Earth does not see that probe traveling at 180% of light speed. They see it traveling at approximately 99.4%. The mathematics reshapes itself around the limit. It bends, it compresses, it conspires to ensure that no combination of subluminal velocities ever produces a superluminal result. You can try any combination you want. 70% plus 70% yields 94%, not 140. 95% plus 95% gives 99.9%, not 190. The formula is rigorously exact, and it has been tested in particle accelerators where beams of protons collide at combined energies that would classically sum to far beyond light speed. The resulting measurements always confirm the relativistic formula. No exception has ever been observed, not once. Not in over a century of increasingly precise experiments conducted in dozens of countries. This means you cannot outmaneuver the speed limit by stacking boosts. You cannot build a ship that accelerates to 90% of light speed, then launches a second ship that accelerates to 90% relative to the first, hoping the second ship has reached 180% relative to Earth. The Lorentz transformation forbids it. Each additional increment of velocity purchases less progress than the one before. The returns are not merely diminishing, they are asymptotically diminishing, approaching zero, becoming infinitely expensive per unit of additional speed gained. The universe behaves like a wall of rubber that stretches away from you. The harder you push against it, you can push forever. You can spend every joule of energy in existence. The wall moves, the gap between you and the speed of light shrinks, but it never closes. And this brings us to the deepest truth hidden inside the Lorentz transformation. The speed of light is not just a speed limit in the way that a posted speed limit restricts drivers on a highway. A highway speed limit is enforced by external authority, a police officer, a traffic camera, a penalty applied from outside the system. You can exceed a highway speed limit if you choose to accept the consequences. The light speed limit carries no external enforcement because it needs none. It is not a rule imposed on space-time. It is a property of space-time. It does not restrict what objects can do within the universe. It defines what the universe is. Asking why nothing can go faster than light is like asking why triangles cannot have four sides. The question contains a misunderstanding of what the terms mean. A triangle with four sides is not a forbidden triangle. It is not a triangle at all. Similarly, an object with mass moving at the speed of light is not a forbidden state of motion. It is a state that does not exist within the mathematical framework describing our universe. And that framework locks away every star in the night sky. Alpha Centauri, the nearest star system to our Sun, sits approximately 4.37 light-years from Earth. Light itself, the fastest thing the universe permits, requires more than 4 years to cross that distance. A light-year equals roughly 5.88 trillion miles. So the nearest star is about 25.7 trillion miles away. Every other star system in existence is farther. Barnard's star, 6 light-years. Wolf 359, 7.9 light-years. Sirius, the brightest star in the sky, 8.6 light-years. The brightest stars visible to the naked eye on a clear night range from a few light-years to many hundreds of light-years distant. The scientifically interesting stellar neighborhoods where we might find habitable worlds are typically tens to hundreds of light-years away. The exoplanets that have excited the most public interest, worlds in the TRAPPIST-1 system, for example, sit about 40 light-years distant. Kepler 452b, once called Earth's cousin, lies roughly 1,400 light-years away. The center of the Milky Way lies 26,000 light-years from Earth. The far edge of our galaxy extends roughly 50,000 light-years beyond that. Even at the absolute cosmic speed limit, crossing the galaxy would require 100,000 years of continuous travel. But nothing with mass can reach that speed. Nothing with mass can even approach it closely without slamming into consequences that escalate beyond all rational comprehension. Those consequences have nothing to do with speed as we commonly understand it. Speed is the surface symptom. The true disease lies deeper. The Lorentz factor does not merely affect clocks and rulers. It acts with identical mathematical force on the energy required to accelerate any object. As velocity climbs toward the speed of light, the energy necessary to achieve each additional increment of speed follows the same curve as the Lorentz factor, rising gently at first, climbing steeply in the middle, then surging almost vertically toward infinity near the boundary. The speed of light is not merely a speed limit, it is an energy limit, a thermodynamic cliff face that rises without bound as ambition increases. The universe does not just forbid you from reaching light speed, it makes the cost of approaching light speed grow without limit, measured in a currency that the laws of physics themselves define, and that no technology can manufacture from nothing. Everything discussed so far describes only the preamble. The real devastation begins when the Lorentz factor meets the most powerful and most consequential equation in the history of physical science. An equation formulated by the same 26-year-old Peyton Clark who uncovered all of this. An equation that connects mass to energy through a constant so staggeringly large that even a small handful of ordinary matter contains enough energy to obliterate a city. That equation is E equals mc squared. And what it does to the mathematics of starflight is not discouraging. It is not pessimistic. It is annihilating. Einstein wrote E equals mc squared in 1905, the same year he published special relativity. It may be the most recognized equation in the history of science. It appears on t-shirts and coffee mugs and posters in college dorm rooms. It has been referenced in thousands of films, books, and songs. Politicians have quoted it in speeches about innovation. Artists have incorporated it into paintings and sculptures. Most educated adults on the planet can recite it from memory. Almost nobody understands what it actually says. The equation is treated as a symbol of genius rather than as a statement about physical reality. But it is a statement about physical reality. And what it says is the single most important reason why interstellar travel is physically impossible. The equation states that energy equals mass multiplied by the speed of light squared. That sounds simple, elegant even. It is not. The speed of light is approximately 186,000 miles per second. Squaring that number produces a figure so enormous that it breaks human intuition. The speed of light squared is approximately 34.7 billion in units of miles squared per second squared. When you convert to standard scientific units, c squared equals approximately 9 times 10 to the 16th power meters squared per second squared. That is 90 quadrillion. This number is the conversion factor between mass and energy. It is the exchange rate at which the universe converts between these two forms of the same underlying substance. It tells you how much energy is locked inside a given amount of matter. And it tells you that even an absurdly small amount of matter contains an almost incomprehensible amount of energy. Consider 1 kilogram of any substance. A bag of flour, a textbook, a liter of water. According to Einstein's equation, that single kilogram contains approximately 90 quadrillion joules of energy. To put that in perspective, the largest nuclear weapon ever detonated was the Tsar Bomba, tested by the Soviet Union in 1961. It released approximately 210 quadrillion joules. That devastating explosion, powerful enough to shatter windows 1,000 kilometers away, generate a mushroom cloud that rose 65 kilometers into the atmosphere, released the energy equivalent of roughly 2.3 kilograms of matter, fully converted into energy. Not 2.3 kilograms of uranium, not 2.3 kilograms of plutonium, 2.3 kilograms of anything. The equation does not care what the mass is made of. Hydrogen, iron, wood, cheese. Every kilogram of matter in the universe contains the same 90 quadrillion joules. The atomic bomb that destroyed Hiroshima converted less than 1 gram of matter into energy. 1 gram, about the mass of a paperclip. That single gram, fully transformed into energy according to E equals mc squared, released energy equivalent to roughly 15,000 tons of TNT, leveling an entire city in an instant. This is what the equation means. Mass is stored energy. Energy is liberated mass. They are the same thing measured in different units, connected by a conversion factor so large that even microscopic quantities of matter correspond to city-destroying quantities of energy. Einstein did not discover a new source of power. He discovered that mass itself is power, concentrated to a degree that makes every other energy source in human experience look trivial. Now here is where this equation meets the Lorentz factor and produces the result that destroys the dream of starflight. The energy we have been discussing so far is rest energy. The energy contained inside a stationary object by virtue of its mass alone. But when an object moves, it also carries kinetic energy. At everyday speeds, kinetic energy is calculated using the familiar classical formula, 1/2 times mass times velocity squared. A car driving at 60 miles per hour carries a modest amount of kinetic energy. Double the speed and the energy quadruples. The relationship is simple, predictable, and well-behaved. But at velocities approaching the speed of light, the classical formula becomes dangerously wrong. It vastly underestimates the true energy because it ignores relativistic effects. The correct formula for the total energy of a moving object at any speed is the rest mass energy multiplied by the Lorentz factor. The kinetic energy alone, the energy you must supply to get the object moving, equals the rest mass energy multiplied by the Lorentz factor -1. This is where the universe reveals its cruelty. Because the Lorentz factor climbs toward infinity as velocity approaches light speed, the kinetic energy required to push even a tiny mass to that velocity also climbs toward infinity. Let us trace this curve with concrete numbers. Take a spacecraft with a mass of 1,000 kilograms, about the size of a small car. At rest, this ship contains approximately 9 times 10 to the 19th joules of energy locked in its mass. Now let us see what it costs to move it. To accelerate this 1,000 kilogram craft to 10% of the speed of light, roughly 30,000 kilometers per second, the required kinetic energy is approximately 4.5 times 10 to the 17 joules. That is 450 quadrillion joules. For perspective, the total energy consumption of all human civilization in an entire year is approximately 5.8 times 10 to the 20 joules. So accelerating a single small car to 10% of light speed would require roughly 1,000th of humanity's annual energy budget. That is staggering, but it at least exists on a scale that is conceivable. A sufficiently advanced civilization might, with extraordinary effort, produce this much energy for a single mission. The number is enormous, but finite and comprehensible. Now pushed to 50% of the speed of light. The Lorentz factor at this velocity is approximately 1.155. The required kinetic energy jumps to about 1.4 times 10 to the 19 joules. That is 14 quintillion joules, roughly 1/40th of the annual energy consumption of all human civilization, consumed in a single act of acceleration. To push a single object the mass of a small car to half the speed of light, not a starship carrying passengers and life support, not a vessel equipped with food, water, recycling systems, and radiation shielding. A bare 1,000 kilogram object with nothing aboard, no crew, no instruments, no structure beyond the minimum needed to hold together, just mass, accelerated to half of light speed, and we have already consumed a substantial fraction of what our entire species produces in a full year of collective industrial effort spanning every nation on Earth. The number has moved from staggering to sobering, and we are only at 50%. Now pushed to 90% of light speed, the Lorentz factor reaches 2.29. The kinetic energy climbs to approximately 1.16 times 10 to the 20th joules. That is 116 quintillion joules, roughly 1/5 of the total annual energy production of all human civilization. 1/5 of everything. Every power plant, every dam, every nuclear reactor, every solar panel, every barrel of oil burned across the globe in 12 months. And this 1,000 kilogram object has consumed 1/5 of it in a single acceleration for the same small car mass payload. The curve has bent sharply upward. Each incremental increase in velocity costs dramatically more than the last, and the real horror has not even started yet. At 99% of the speed of light, the Lorentz factor reaches 7.09. The kinetic energy soars to approximately 5.5 times 10 to the 20th joules. That is roughly equal to the total annual energy consumption of every civilization on Earth combined. The entire output of every power plant, every reactor, every combustion engine, every energy source operated by 7 billion people across an entire calendar year, poured into accelerating a single object that weighs less than a compact car, and we are still nowhere near the speed of light itself. At 99.9%, the Lorentz factor hits 22.4. The energy requirement surges to approximately 1.9 times 10 to the 21st joules. At 99.99%, the Lorentz factor exceeds 70, and the energy climbs past 6 times 10 to the 21st joules. Each additional decimal of nines roughly triples the energy requirement. The progression does not slow down, it accelerates. Every step closer to the speed of light costs more than all previous steps combined. This is what an asymptotic curve looks like when it is denominated in energy. The cost of the final fraction of a percent exceeds everything that came before it. And remember, these calculations describe accelerating 1,000 kilograms, 1 metric ton, a real interstellar spacecraft capable of carrying humans would need to mass at minimum tens of thousands of kilograms. More realistically, hundreds of thousands. The International Space Station masses approximately 420,000 kilograms, and it cannot sustain a crew indefinitely, does not carry its own propulsion for interstellar velocities, and was never designed for the rigors of decades-long spaceflight. Scale the energy requirements from our 1,000 kilogram example up to a plausible crewed starship of 100,000 kilograms, and every number we calculated multiplies by a factor of 100. The energy needed to push such a vessel to 90% of light speed becomes roughly 20 times the annual energy production of human civilization. Not a percentage of it. 20 times the total. The entire output of every power plant, every dam, every solar panel, every nuclear reactor, every burning piece of coal and gas on Earth for an entire year multiplied by 20. But energy production is ultimately a matter of technology. One might argue that a civilization far more advanced than ours could generate such quantities. So, let us escalate the comparison beyond human capability and into the realm of astrophysics itself. Consider not what humanity produces, but what nature produces. Our sun radiates approximately 3.8 times 10 to the 26th joules per second. That is 380 trillion watts. Every second of every day, continuously, for the last 4.5 billion years, in one full year, the sun emits roughly 1.2 times 10 to the 34th joules of total energy. That is a number so large that writing it in full would require 34 digits. Now ask what fraction of the sun's annual output would be required to accelerate a modest starship to a reasonable fraction of light speed. For a 100,000 kilogram vessel pushed to 90% of light speed, the energy requirement is approximately 1.2 times 10 to the 22nd joules. That represents about 1 trillionth of the sun's annual energy output. 1 trillionth sounds like a small fraction, and in relative terms it is, but capturing even 1 trillionth of the sun's output in a usable form is far beyond anything human civilization has ever attempted. You would need to construct a solar collection apparatus of enormous size, position it in close solar orbit, operate it continuously for years, and somehow convert captured radiant energy into directed kinetic energy with near-perfect efficiency. The total collecting area required, even at Mercury's orbital distance, would span thousands of square kilometers. No such technology exists, and the engineering challenges are beyond anything humanity has seriously contemplated. But the truly devastating comparison is not about production, it is about content. Mass energy equivalence tells us how much energy is locked inside matter itself. The entire Earth has a mass of approximately 6 times 10 to the 24th kilograms. According to E equals mc squared, the total energy content of planet Earth, if every single atom were perfectly and completely converted into energy, equals approximately 5.4 times 10 to the 41st joules. Accelerating a modest 100,000 kilogram spacecraft to 99.9% of light speed would require roughly 1.9 times 10 to the 23rd joules. That is still a vanishingly tiny fraction of Earth's total mass energy content. But now scale the ambition upward to something resembling a real interstellar mission. Not a bare probe, but an actual colony ship. Something capable of sustaining a viable population of thousands of passengers over decades or centuries of travel, with all the food production, water recycling, atmospheric management, medical facilities, manufacturing capability, and structural redundancy that implies. Such a vessel might realistically mass tens of millions of kilograms or more. Push a 10 million kilogram colony ship to 99.9% of light speed, and the energy cost enters the range of 10 to the 25th joules. To generate that much energy through complete mass-to-energy conversion, you would need to annihilate roughly 200 million kilograms of matter. That is more than the mass of a large ocean liner, converted entirely into energy with perfect efficiency, using a process that does not exist and may never exist, because complete mass-to-energy conversion of ordinary matter is not something any known physics can achieve outside of matter-antimatter annihilation. And antimatter introduces its own impossibilities. Antimatter is the only substance in the known universe that can convert mass entirely into energy upon contact with normal matter. When a particle of matter meets its corresponding antimatter counterpart, both are completely annihilated and their combined mass is released as high-energy gamma-ray photons traveling at the speed of light. 1 kilogram of antimatter, annihilating with 1 kilogram of matter, produces approximately 1.8 times 10 to the 17 joules. The conversion is complete. Every bit of mass becomes energy. No waste. No inefficiency. No residual ash or spent fuel. It is the theoretical ceiling of energy extraction from matter. Nothing in physics can do better. But producing antimatter is extraordinarily difficult and expensive. Current particle accelerators at facilities like CERN produce antimatter in quantities measured in nanograms per year. A nanogram is 1 billionth of a gram. To visualize this, the total amount of antimatter ever produced by all the particle accelerators in human history, combined, would not be enough to heat a cup of coffee. At present production rates, accumulating a single gram of antimatter would require approximately 100 billion years. That is roughly 7 times longer than the current age of the universe. And a single gram would be comically insufficient for an interstellar mission requiring tens of thousands of kilograms of the substance. Even if antimatter production could be scaled up by factors of trillions, the energy required to produce the antimatter in the first place would exceed the energy the antimatter releases when annihilated. You cannot create energy from nothing. The first law of thermodynamics forbids it. Antimatter is not a source of energy. It is a storage medium. And it is one that currently costs vastly more energy to fill than it returns when emptied. This is not simply an engineering bottleneck that better technology will resolve. This is a thermodynamic constraint imposed by conservation laws. The rocket equation makes everything exponentially worse. In any rocket, regardless of its propulsion system, the vehicle must carry its own fuel. That fuel has mass. That mass must also be accelerated along with the payload, which requires more fuel, which has more mass, which requires still more fuel. This circular dependency is described by the Tsiolkovsky rocket equation, first derived by the Russian mathematician Konstantin Tsiolkovsky in 1903. In its classical form, the equation reveals that the mass of fuel required grows exponentially with the desired velocity change relative to the exhaust velocity of the propellant. This is not a gentle exponential. It is ruthless. Double the velocity and you do not merely double the fuel. You square the exponent. The relationship is logarithmic in reverse. The fuel to payload mass ratio increases exponentially as the target velocity rises. At the velocities relevant to interstellar travel, this exponential becomes a vertical cliff. In a relativistic context, the rocket equation becomes even more punishing. At relativistic speeds, the exhaust velocity of the propellant matters enormously. Even if you could somehow use a perfect photon drive, expelling pure light as exhaust at the maximum possible velocity, the relativistic rocket equation still demands fuel masses that grow exponentially with the target Lorentz factor. For a photon rocket accelerating to 90% of light speed, the ratio of initial mass to final payload mass is approximately 4.7 to 1. That means for every kilogram of payload, you need 4.7 kilograms of fuel at departure. At 99% of light speed, the one-way mass ratio climbs to approximately 14 to 1. But this is the optimistic case, assuming a perfect photon drive, which does not exist. Any realistic propulsion system with exhaust velocity lower than light speed demands far worse ratios. For a photon rocket reaching 99.9% of light speed, the one-way mass ratio exceeds 45 to 1. Each additional decimal of nines does not merely increase the fuel requirement, it multiplies it by another order of magnitude. And these ratios only describe acceleration. They do not include slowing down at the destination. This exponential stacking is the mathematical signature of a problem that cannot be solved by improvement. You cannot engineer your way past an exponential. This is not a statement of pessimism. It is a theorem of mathematics. Every improvement in engine efficiency buys a linear gain that is immediately swallowed by the exponential growth of fuel requirements. Build an engine 10 times more efficient, and the exponential simply pushes the wall back by 1 increment. 100 times more efficient, 2 increments. 1,000,000 times more efficient, 6 increments. The exponential always wins. It always catches up. It always overwhelms any finite improvement in technology because that is what exponential functions do. They outrun every polynomial and every linear function given enough distance along the curve. The curve toward light speed provides exactly that distance. This exponential fuel problem creates a cascading failure mode that traps every conceivable starship design in a spiral of growing mass. Start with a payload, a crew module, scientific instruments, communication equipment. Add the fuel required to accelerate that payload. That fuel adds mass to the total vehicle. Now add more fuel to accelerate the additional fuel mass. That additional fuel adds still more mass. Continue this cycle until the mass of fuel dominates the entire vehicle by factors of hundreds or thousands. Now the structural supports needed to contain all that fuel must be stronger, which means heavier. The tanks, whether they hold antimatter, fusion fuel, or any other propellant, must be larger and more robust. The engines needed to process and expel that fuel must be more powerful and therefore heavier. The thermal management systems needed to handle the waste heat generated by engines burning fuel at rates measured in kilograms per second must be vastly more capable and therefore heavier. The radiation shielding needed to protect the crew from the engine's own emissions, which at these power levels would include torrents of gamma radiation and high-energy particle spray, must be thicker and therefore heavier. Every component of the spacecraft grows in response to the fuel requirement, and every gram of growth in component mass feeds directly back into the fuel calculation, demanding still more fuel. The entire design spirals outward without converging on a stable solution. Engineers call this the tyranny of the rocket equation, and in the context of interstellar travel at relativistic speeds, it is not a tyranny that can be overthrown by cleverness or revolution. It is a mathematical identity, a tautology, woven into the relationship between momentum, mass, and energy conservation. It applies to every propulsion concept ever devised and every propulsion concept that could ever be devised within the framework of known physics. There is a reason why every serious study of interstellar travel, conducted by major aerospace organizations and national space agencies, has concluded with the same quiet admission. The energy requirements are not challenging. They are not merely difficult. They are prohibitive. Not prohibitive in the sense that they exceed current budgets or current technology. Prohibitive in the sense that they exceed the energy content of entire worlds. The numbers do not bend. They do not negotiate. They do not leave cracks through which ingenuity might slip. They close every door, lock every window, and brick over every opening with the calm mathematical certainty of an equation that has been tested in every particle accelerator on the planet and has never been wrong. Some people hear these numbers and respond with optimism rooted in historical analogy. They point out that a medieval peasant could not have imagined a nuclear reactor. They argue that a Roman engineer could not have conceived of a jet engine. They suggest that future physics might discover entirely new energy sources as far beyond nuclear energy as nuclear energy is beyond burning wood. Perhaps some undiscovered quantum phenomenon will unlock unlimited energy. Perhaps dark energy can somehow be harnessed. Perhaps vacuum energy can be extracted from empty space. These speculations are understandable. They reflect the same pattern-matching instinct that has served humanity well throughout history. But this argument fundamentally misunderstands the nature of the constraint. The energy requirements we have described are not derived from any particular technology or any particular energy source. They are derived from the Lorentz transformation, from the geometry of space-time itself. It does not matter where the energy comes from, whether it comes from chemical reactions, nuclear fission, nuclear fusion, antimatter annihilation, or some as yet undiscovered source, the amount needed to push a given mass to a given fraction of light speed is fixed by special relativity. No future discovery can reduce that amount, because the amount is not determined by our technology. It is determined by the structure of the universe. Discovering a better energy source is like discovering a faster way to fill a swimming pool. It does not matter whether you use a garden hose, a fire hose, or a river diverted through an industrial pipe. The pool does not get smaller because you improved the filling mechanism. The volume of water needed to fill it is fixed by the dimensions of the pool. Those dimensions are determined by whoever built the pool, and in this case, the pool was built by the Lorentz transformation. The energy required to accelerate a given mass to a given velocity is the pool. The Lorentz factor sets its depth, and that depth increases toward infinity as the target velocity approaches light speed. No future technology can change the dimensions of that pool, because the dimensions are properties of space-time, not properties of human engineering. A civilization a million years more advanced than ours would face the same pool, the same depth, the same infinite wall at the boundary. Their hoses might be bigger. The pool remains the same size. Let us be precise about what this means. If you want to accelerate a mass m to a velocity v that represents a significant fraction of the speed of light, the energy you must supply is determined by a specific mathematical function of v. That function is fixed. It was derived by Einstein in 1905 and has been confirmed by every relevant experiment conducted since. No future civilization, no matter how advanced, can change this function. They can find more efficient ways to generate energy. They can find more efficient ways to convert energy into thrust, but they cannot reduce the total energy that the laws of physics demand for that acceleration. The bill is written in the language of space-time, and space-time does not offer discounts. The implications cascade outward from this central fact like cracks spreading from a point of impact. Every proposal for interstellar travel that involves moving a physical object at a meaningful fraction of light speed runs directly into this energy wall. It does not matter if the proposal uses sails, beams, magnetic fields, or engines of any design. If mass is being accelerated to relativistic speed, the energy cost follows the Lorentz curve. The cost is not determined by the method. It is determined by the destination on that curve. And every interesting destination, every fraction of light speed that would make interstellar distances crossable within human timescales, sits on the steep part of the curve where energy costs are measured in fractions of stellar output. But even this brutal accounting contains a hidden assumption that makes the true situation far worse than anything we have calculated so far. Everything we have discussed so far describes only the energy needed to accelerate the spacecraft. Only the outbound push, the departure. The numbers we computed assume that getting the ship up to speed is the entire challenge. They assume that once the spacecraft reaches its target velocity, the hard part is over. This assumption is spectacularly, catastrophically wrong. There is a question we have not yet asked, a question so obvious that it hides in plain sight, and it is a question so devastating that it doubles or squares every number we have calculated. How does the ship stop? And even if it could stop, how does it survive the journey? Because the space between the stars is not the empty, benign void that popular imagination depicts. It is a shooting gallery. At relativistic speeds, the thin gas and microscopic dust scattered between the stars transform into a continuous bombardment of radiation and high-energy impacts that would shred any physical structure ever built by human hands. The deceleration problem and the interstellar gauntlet together form a second wall behind the energy wall, and they are the subject of what comes next. Imagine you have somehow solved every problem described so far. Imagine a civilization so advanced it can generate energy on scales that rival stellar output. Imagine engines so efficient they approach theoretical perfection. Imagine fuel tanks built from materials that do not exist yet, containing propellants that border on the magical. Imagine all of that. Now picture the spacecraft at the midpoint of its journey. It has accelerated for years. It has consumed unimaginable quantities of energy. It has reached 90% of the speed of light and is now hurtling through the interstellar void at approximately 168,000 miles per second. The destination star is growing brighter ahead. The mission, against all odds, appears to be succeeding. And then a simple question arises that demolishes everything. How does the ship stop? This question is so obvious that it seems absurd to call it overlooked. But in popular discussions of interstellar travel, in science fiction films and novels and breathless technology articles, it is almost universally ignored or trivialized. Ships arrive at distant stars and simply park in orbit as though braking from relativistic velocity were no different from pulling a car into a driveway. A character flips a switch and the ship decelerates smoothly into the destination system. The reality is that stopping is not a secondary problem appended to the journey as an afterthought. It is not a minor engineering footnote to be solved after the main challenge of acceleration has been addressed. Stopping is a problem equal in magnitude to the entire outbound acceleration. And in many realistic mission architectures, it is actually worse because the fuel for stopping must itself be accelerated during departure. Deceleration at relativistic speeds requires the same physics, the same engines, and the same staggering energy expenditure as acceleration. To shed velocity, the spacecraft must rotate 180 degrees and fire its engines in the direction of travel, applying sustained thrust against its own forward motion for a duration, and at an intensity comparable to the original boost phase. Every single joule of kinetic energy gained during acceleration must be removed during deceleration through active expenditure of onboard propellant. There is no shortcut around this requirement. There is no coasting gently into the destination system on residual momentum. There is no aerobraking against an interstellar medium that is trillions of times thinner than Earth's atmosphere. There is no gravitational capture maneuver that can absorb the kinetic energy of an object moving at a significant fraction of light speed. The ship must carry its own brakes, and those brakes are made entirely of fuel. This is where the mathematics becomes genuinely cruel. The fuel required for deceleration must be on board the spacecraft from the moment it leaves Earth. That deceleration fuel has mass. That mass must be accelerated along with everything else during the outbound boost, which means the acceleration phase must account not only for the payload and the acceleration fuel, but also for the deceleration fuel. The mass of the deceleration fuel increases the total mass that must be accelerated, which increases the amount of acceleration fuel required, which increases the total mass further. The exponential rocket equation, already devastating in the context of one-way acceleration, now compounds upon itself. The exponent does not double, it squares. For a photon rocket, the theoretical best case, the mass ratio for a mission that accelerates to a target velocity and then decelerates back to rest, is the square of the mass ratio for acceleration alone. At 90% of light speed, the one-way mass ratio for a perfect photon rocket is approximately 4.7 to 1, meaning you need 4.7 kilograms of fuel for every kilogram of payload. Squaring that for a complete acceleration-deceleration profile gives approximately 22 to 1. 22 kilograms of photon fuel for every kilogram of payload delivered to the destination at rest. A 100,000 kilogram spacecraft would require 2.2 million kilograms of fuel at departure. But 90% of light speed, while dramatic by human standards, is not fast enough to make interstellar distances manageable within a single human lifetime for the crew on board. To cross the 4.37 light years to Alpha Centauri at 90% of light speed takes approximately 4.9 years from the perspective of a stationary observer on Earth, and about 2.1 years from the perspective of the crew due to time dilation. That is tolerable. But for more distant targets, say a star 40 light years away, the journey at 90% of light speed takes 44 years Earth time and about 19 years ship time. A crewed mission to such a target would require pushing closer to the speed of light to reduce the subjective travel time to something a human crew could survive. At 99% of light speed, the one-way mass ratio for a photon rocket climbs to approximately 14 to 1. The round-trip acceleration-deceleration ratio squares to roughly 196 to 1, nearly 200 kilograms of fuel for every kilogram that arrives at the destination. At 99.9%, the one-way ratio reaches approximately 45 to 1, and the squared deceleration profile demands a mass ratio exceeding 2,000 to 1. 2,000 kilograms of perfect photon fuel for every single kilogram of payload. A modest 100,000 kilogram ship would need 200 million kilograms of fuel, 200,000 metric tons. That is roughly twice the mass of the largest aircraft carrier ever built, except this mass is not steel and electronics. It is fuel that must be manufactured, stored at extremes of density and temperature, and fed into engines that do not yet exist and may never exist. And these numbers assume a perfect photon drive. The photon rocket is a theoretical construct in which the exhaust consists entirely of photons traveling at the speed of light, which is the highest possible exhaust velocity permitted by physics. Any real propulsion system has a lower exhaust velocity, which means worse mass ratios. For a fusion rocket expelling plasma at 10% of light speed, the mass ratios climb by additional orders of magnitude at every target velocity. The numbers leave the realm of engineering and enter the realm of absurdity. The fuel mass exceeds the mass of planets. The energy budget exceeds the output of stars. And none of this accounts for the structural mass of the fuel tanks, the engines, the thermal systems, the crew habitat, or anything else that makes a spacecraft, rather than a theoretical point mass in an equation. There is a class of proposed solutions that attempts to sidestep the deceleration fuel problem. Most commonly cited is the magnetic sail, or MagSail. The concept involves deploying an enormous superconducting loop after the cruise phase that generates a magnetic field, interacting with the interstellar medium's charged particles, creating drag. In principle, this drag could gradually slow the spacecraft without expending onboard fuel. The physics is real. Charged particles in the interstellar medium would indeed interact with a sufficiently powerful magnetic field, but the practical numbers are discouraging. The interstellar medium has a density of roughly 1 hydrogen atom per cubic centimeter. At 90% of light speed, a MagSail would need to sweep a cross-sectional area measured in hundreds of square kilometers to generate meaningful deceleration force on a 100,000 kilogram vehicle. The superconducting loop required to produce such a field would itself mass thousands of kilograms, and maintaining superconducting temperatures in the interstellar environment while being bombarded by relativistic particle impacts presents engineering challenges that border on the fantastical. Even optimistic analyses suggest that MagSail braking from 90% of light speed would require decades of continuous deceleration over a distance of several light years. The ship would need to begin braking halfway through its journey, which means it spends only the first half accelerating and the entire second half decelerating. The effective cruise velocity for the overall trip drops dramatically, extending journey times and undermining the entire purpose of traveling at relativistic speed. Another proposed solution is to use the destination star's light pressure for braking. Robert Forward described a mission architecture in 1984 in which a laser-pushed light sail separates into 2 sections near the destination. The outer ring reflects laser light back onto the inner section, decelerating it. The concept is ingenious on paper, but it requires a laser array of extraordinary power, operating continuously from the home system across distances of light years, maintaining beam coherence and targeting accuracy over those distances for years or decades. The power requirements for such a laser are themselves a significant fraction of stellar output. The scheme does not eliminate the energy problem. It relocates it from onboard fuel to a home system laser installation of almost unimaginable scale. And it introduces new failure modes. Any interruption in the laser beam during the deceleration phase would leave the payload hurtling past the destination with no way to stop. Gravitational braking is sometimes mentioned as yet another alternative. Perhaps a spacecraft could swing around the destination star in a tight hyperbolic orbit, using gravitational forces to shed velocity the way interplanetary probes like Voyager and Cassini have used planetary flybys to adjust their trajectories within our solar system. This technique is proven and elegant at the velocities relevant to solar system exploration, where spacecraft travel at tens of kilometers per second, and planets provide gravitational wells deep enough to produce meaningful velocity changes. At relativistic speeds, gravitational braking fails completely and utterly. A spacecraft approaching a sun-like star at 90% of light speed carries kinetic energy that dwarfs the gravitational binding energy available from any conceivable stellar flyby. The maximum velocity change achievable through a gravitational assist is fundamentally limited by the escape velocity of the body being used for the maneuver, which for a sun-like star is approximately 617 kilometers per second at the stellar surface. That is roughly 0.2% of the speed of light. Attempting a gravitational braking maneuver against a spacecraft traveling at 90% of light speed would reduce its velocity by an amount so small it would be lost in rounding errors. It would be like trying to stop a speeding freight train by placing a single sheet of tissue paper across the tracks. The scales are not merely mismatched, they inhabit different universes of magnitude. The deceleration problem is not an oversight in mission planning. It is a direct consequence of the same relativistic energy scaling we have already described. Kinetic energy at relativistic speeds is enormous, and removing that energy requires the same expenditure that putting it there demanded. No trick of orbital mechanics, no clever sail design, no magnetic interaction with the interstellar medium can circumvent this fundamental accounting. Energy is conserved, momentum is conserved. A ship that accelerated to relativistic speed must expend comparable energy to decelerate, and the fuel for that expenditure must ride along from the beginning, compounding the exponential mass problem at every stage. But the deceleration trap, devastating as it is, represents only half of the nightmare awaiting a relativistic spacecraft during its journey. The other half comes from the space between the stars, and what the space between the stars does to a ship moving at a significant fraction of light speed is nothing short of lethal. The common image of interstellar space is emptiness, a vast, serene, perfect vacuum stretching between the stars with absolutely nothing to obstruct a spacecraft's path. This image pervades science fiction and popular science alike. Artists render the spaces between stars as smooth black voids. Writers describe interstellar cruises as peaceful intervals of quiet drifting. The public imagination pictures the journey between stars as fundamentally uneventful, a long wait in empty darkness before the destination appears ahead. This image is dangerously wrong. Interstellar space is not empty. It contains matter, not much by any terrestrial or even planetary standard, but enough to become catastrophically dangerous at relativistic velocities. The interstellar medium consists primarily of hydrogen atoms and ions, scattered at an average density of approximately 1 atom per cubic centimeter in the general galactic disk, with localized variations ranging from as sparse as 0.1 atoms per cubic centimeter in hot bubble regions to several thousand atoms per cubic centimeter in dense molecular clouds. That sounds like nothing. 1 atom per cubic centimeter is a vacuum so extreme that it surpasses even the best vacuum chambers on Earth. The finest ultra-high vacuum systems in laboratory settings achieve densities of roughly 10,000 molecules per cubic centimeter. Interstellar space is emptier than that by a factor of 10,000. It seems absurd to worry about individual atoms when dealing with spacecraft built from tons of solid material, but velocity changes everything. At relativistic speeds, each individual hydrogen atom transforms from a harmless wisp of matter into a projectile carrying tremendous kinetic energy. The kinetic energy of a particle scales with the Lorentz factor, and at 90% of light speed, the Lorentz factor is 2.29. A single hydrogen atom massing approximately 1.67 times 10 to the negative 27 kilograms, striking a surface at 90% of the speed of light, carries a kinetic energy of approximately 1.7 times 10 to the negative 10 joules. That is the energy of a single atom. It sounds small because it is small in absolute terms, but the spacecraft is not encountering one atom. It is encountering roughly one atom per cubic centimeter along its entire path, and it is sweeping through that medium at 168,000 miles per second. A spacecraft with a forward cross-sectional area of 10 square meters, traveling at 90% of light speed, sweeps through a volume of approximately 2.7 quadrillion cubic centimeters per second. At a density of one atom per cubic centimeter, that means the ship encounters roughly 2.7 quadrillion hydrogen atoms every second, each carrying approximately 1.7 times 10 to the negative 10 joules. The total power deposited onto the forward surface of the spacecraft reaches approximately 46 kilowatts per square meter, even before accounting for the full violence of the nuclear scale interactions involved. At relativistic speeds, the collision physics becomes far more extreme than simple kinetic energy transfer. Each hydrogen atom, when it strikes the hull at 90% of light speed, does not simply bounce off or embed itself in the surface. It undergoes nuclear scale interactions. The collision energy per nucleon exceeds the binding energy of atomic nuclei. The hydrogen atoms effectively become a beam of relativistic protons, bombarding the spacecraft's forward surface with energies comparable to those produced in particle accelerators. Each proton impact at 90% of light speed carries an energy of approximately 1.2 giga-electron volts. For comparison, the protons in the Large Hadron Collider at CERN reach energies of 6.5 tera-electron volts, roughly 5,000 times higher. But the LHC produces a narrow beam of carefully controlled particles in a vacuum pipe. A relativistic spacecraft encounters an omnidirectional bath of these impacts across its entire forward surface, continuously, for months or years. The cumulative radiation dose is staggering. At 90% of light speed, the proton flux on the forward surface amounts to approximately 2.7 times 10 to the 14th protons per square meter per second. Each proton deposits energy as it penetrates the hull material, creating cascades of secondary particles, neutrons, pions, gamma rays, and electromagnetic showers that penetrate far deeper than the original proton. The effective radiation dose behind even substantial shielding reaches levels that would be lethal to biological organisms within minutes. Not hours, not days, minutes. The forward section of any relativistic spacecraft becomes a kill zone of ionizing radiation that no known material can adequately shield against without adding mass that feeds back into the exponential fuel problem. Increasing the velocity makes this dramatically worse. At 99% of light speed, the Lorentz factor reaches 7.09. The energy per proton impact climbs to approximately 6.6 giga-electron volts. The particle flux increases proportionally with velocity, meaning the spacecraft sweeps through the medium faster and encounters more atoms per second. The radiation environment at the forward hull intensifies by roughly an order of magnitude compared to 90% of light speed. At 99.9%, the situation becomes almost incomprehensible. Each hydrogen atom carries energy equivalent to a heavy cosmic ray primary, and the flux density reaches levels comparable to standing inside a particle accelerator beamline. No shielding material exists that can protect a crew under these conditions without itself massing thousands or tens of thousands of kilograms, which of course must be accelerated and decelerated along with the rest of the ship. And hydrogen atoms are not the only threat lurking in the interstellar void. The interstellar medium also contains dust grains. These are microscopic particles of silicate minerals and carbon compounds, forged in the outer atmospheres of dying stars and dispersed throughout the galaxy by stellar winds and supernova explosions. They are typically irregular in shape, ranging from a few nanometers to a few micrometers in diameter. To the naked eye, even 1 million of them gathered together would be invisible. Their density is much lower than that of hydrogen atoms, roughly 1 grain per 100,000 cubic meters in typical interstellar space. That is an almost incomprehensible emptiness. billions of cubic meters of space containing a single speck of mineral dust. But a single dust grain, even one measuring just 10 micrometers across, roughly 1/5 the width of a human hair, has a mass of approximately 10 to the negative 12 kilograms. At 90% of light speed, such a grain carries a kinetic energy of roughly 100,000 joules. That is comparable to a small explosive charge. A 10 micrometer speck of invisible dust, smaller than a blood cell, hits the ship with enough energy to vaporize a crater in solid steel. Larger grains, 100 micrometers across, roughly the diameter of a fine grain of sand, would carry energies in the range of 100 million joules upon impact, comparable to detonating dozens of kilograms of high explosive against the hull. And while these impacts are rare on a per-second basis, a journey spanning light years means the spacecraft sweeps through an enormous volume of space over the course of months or years. Even at the low average density of interstellar dust, a ship traveling several light years at relativistic speed would accumulate thousands of dust grain impacts, each one a miniature explosion against the hull. The erosion problem is relentless and cumulative. Each dust grain impact excavates a small crater in the forward shielding material. The crater size depends on the grain mass, the impact velocity, and the shielding composition. But at relativistic speeds, even tiny impacts produce disproportionately large damage, because the energy density at the impact point exceeds the structural strength of any known material by orders of magnitude. The impact does not merely dent the surface, it vaporizes a small volume of shielding material, sending a spray of secondary debris backward into the spacecraft structure. Over the course of a multi-year interstellar journey spanning several light years, the cumulative erosion from thousands of dust grain impacts could remove centimeters or even meters of material from the ship's leading surface, depending on the shielding composition, thickness, and the specific dust density along the particular flight path chosen. And dust density is not uniform across the galaxy. Some regions of interstellar space have dust concentrations significantly higher than the average, particularly near the galactic plane. Within the residual expanding shells of old supernova remnants, and in the vicinity of star-forming regions where fresh dust is continuously being produced, a spacecraft unfortunate enough to traverse one of these denser regions, or even a moderately denser than average corridor between two stars, would face dramatically elevated impact rates that could potentially compromise structural integrity and breach shielding layers long before the ship reaches its intended destination. And there is no way to steer around these regions at relativistic speed. Course corrections at 90% of light speed require enormous energy expenditures of their own. The ship is essentially committed to its trajectory from the moment of departure. Whatever lies along that straight-line path between origin and destination, the ship must endure. There is yet another hazard that operates at a completely different wavelength and through an entirely different mechanism. The cosmic microwave background radiation is a bath of photons filling every cubic centimeter of space in the observable universe, left over from the era approximately 380,000 years after the Big Bang, when the universe first became transparent to light. At rest relative to this radiation bath, the cosmic microwave background has an effective temperature of approximately 2.7 Kelvin, just a few degrees above absolute zero, and a peak wavelength deep in the microwave range of the electromagnetic spectrum. It is completely harmless, utterly benign. You are immersed in it at this very moment, and you will never notice it without specialized radio equipment cooled to near absolute zero. But for a spacecraft traveling at relativistic speed, the cosmic microwave background undergoes a dramatic relativistic transformation. Photons arriving from the forward direction are blue shifted to dramatically higher energies due to the Doppler effect. At 90% of light speed, the blue shift factor for head-on photons is approximately 4.4, pushing the peak wavelength from microwaves into the far infrared. At 99% of light speed, the blue shift factor climbs to approximately 14, pushing the peak into the near infrared. At 99.9%, the factor exceeds 44, shifting the peak into visible light and the high-energy tail into ultraviolet and soft X-rays. The forward-facing surface of the spacecraft is being irradiated by blue-shifted cosmic background photons that have been transformed from harmless microwaves into an intense beam of increasingly energetic radiation. This radiation pressure creates a thermal load on the forward shielding that must be managed by the spacecraft's thermal control systems. At 99% of light speed, the effective temperature of the blue-shifted cosmic microwave background, as seen by the ship's forward surface, exceeds 38 Kelvin. That sounds cold, but the radiation flux is concentrated by the relativistic headlight effect into a forward cone, increasing the power per unit area striking the nose of the ship. At higher velocities, the flux intensifies further. Simultaneously, starlight from ahead is blue shifted into ultraviolet and X-ray wavelengths, adding to the radiation burden. The spacecraft is flying into a focused beam of high-energy photons that grows more intense and more penetrating with every increment of additional speed. Now combine every element we have described into a single coherent picture of what a relativistic interstellar mission actually faces. The deceleration fuel that must be carried from departure, compounding the exponential mass ratio into a squared exponent that demands hundreds or thousands of kilograms of fuel for every kilogram of payload. The relativistic hydrogen bombardment that irradiates the forward hull with particle accelerator level proton impacts continuously for years. The interstellar dust grains that strike like bullets and small explosive charges, steadily eroding the shielding over years of continuous transit through the galactic medium. The blue-shifted cosmic microwave background and starlight that bathe the ship in escalating electromagnetic radiation, growing more energetic with every increment of velocity. Each of these problems individually would pose enormous challenges. Together, they form an interlocking web of constraints that tighten with every increase in velocity. Faster ships need more fuel, which means more mass. More mass means stronger engines, which means more mass. More speed means worse radiation, which means more shielding, which means more mass. More mass means more fuel. The cycle feeds itself endlessly, each problem amplifying every other problem in a feedback loop that has no stable equilibrium point at any velocity useful for interstellar travel. And critically, every single one of these constraints arises not from engineering limitations but from physical law. The deceleration energy requirement comes from conservation of energy and the Lorentz transformation. The relativistic proton bombardment comes from the kinetic energy of particles in the interstellar medium, governed by special relativity. The dust grain impacts follow from straightforward Newtonian mechanics scaled to relativistic velocities. The blue-shifted radiation follows from the relativistic Doppler effect, a direct mathematical consequence of special relativity. No future technology can change the energy of a hydrogen atom, traveling at 90% of light speed relative to a spacecraft hull. No future material can violate conservation of energy to absorb that impact without consequence. No future engine design can escape the rocket equation's exponential demand for fuel. These are not engineering walls waiting for better tools. These are the rules of the universe written in the language of mathematics. The ship cannot go fast enough to make the journey short without triggering the energy catastrophe. It cannot carry enough fuel to decelerate without compounding the mass catastrophe. It cannot survive the crossing without shielding that creates still more mass. And every kilogram of additional mass feeds back into every other problem simultaneously. The constraints do not merely add together, they multiply. They form a closed loop from which there is no exit within the known laws of physics. What remains is to ask the final question: is there any escape? Can speculative physics offer a way around these interlocking walls? Can warp drives, wormholes, or other exotic proposals provide what conventional propulsion cannot? And if not, what does it mean to live in a universe where the stars are visible, but permanently, physically, mathematically out of reach? The answer to those questions is what we turn to now. Let us now stand back and look at the full architecture of the prison. We established that the speed of light is not a speed limit imposed on the universe from outside. It is a structural constant embedded in the geometry of space-time itself. The Lorentz factor enforces this limit by driving every relevant physical quantity toward infinity as velocity approaches light speed. Time dilation, length contraction, momentum, and energy all diverge along the same asymptotic curve. There is no velocity at which a massive object reaches the speed of light, because the equations describing motion cease to produce finite answers at that boundary. This is not an engineering challenge. It is a topological feature of the universe we inhabit. We then traced what happens when the Lorentz factor is applied to energy. Einstein's mass-energy equivalence revealed that even tiny amounts of mass contain staggering quantities of energy, and that the kinetic energy required to accelerate any object to a significant fraction of light speed grows along the same divergent curve as the Lorentz factor itself. The numbers escalated from large to absurd to physically meaningless. Accelerating a modest spacecraft to 99% of light speed requires energy comparable to the total annual energy production of human civilization. The relativistic rocket equation compounds this by demanding exponentially growing fuel masses for every increment of target velocity. No energy source, whether it exists today or is discovered 1,000 years from now, can change the amount of energy that the Lorentz transformation demands. The bill is set by space-time, not by technology. We then discovered that even if the energy problem could somehow be overcome, 2 additional walls stand behind it. The deceleration trap doubles or squares the exponential fuel requirement by demanding that the ship carry enough propellant to stop as well as start. And the interstellar medium, far from being the benign vacuum of popular imagination, becomes a lethal gauntlet of relativistic proton bombardment, high-energy dust grain impacts, and blue-shifted cosmic radiation that intensifies with every increment of speed. Every proposed solution to one problem feeds mass back into every other problem, creating an interlocking system of constraints with no stable solution at any velocity useful for crude interstellar travel. These 3 walls are not independent obstacles that might be defeated one at a time. They are manifestations of a single underlying reality, the Lorentz transformation and the conservation laws that govern energy and momentum in relativistic spacetime. They are connected at the level of fundamental physics. You cannot solve the energy problem without making the shielding problem worse. You cannot solve the shielding problem without making the fuel problem worse. You cannot solve the fuel problem without confronting the energy problem again. The constraints form a closed loop, a mathematical cage with no exit that remains open at relativistic velocities. Given this cage, it is natural to ask whether speculative physics offers an escape. If conventional propulsion cannot cross the stars, perhaps unconventional physics can. The 2 most commonly cited speculative proposals are the Alcubierre warp drive and traversable wormholes. Both have captured enormous public imagination over the decades since their conception. Both are grounded in real, peer-reviewed theoretical physics, and both, upon close examination, fail to provide an escape route from the constraints we have described. The Alcubierre warp drive was first proposed in 1994 by the Mexican theoretical physicist Miguel Alcubierre in a paper published in the journal Classical and Quantum Gravity. The concept is elegant and deeply counterintuitive. Instead of moving a spacecraft through space at superluminal velocity, which special relativity forbids, the warp drive would compress space-time in front of the ship and expand it behind the ship. The vessel itself would remain stationary within a bubble of flat space-time, while the bubble moves through the surrounding space-time at arbitrarily high velocity. Because the ship is not moving through local space, it does not violate special relativity. The speed of light limit applies to motion through space, not to the rate at which space itself can deform. The mathematics works. Alcubierre demonstrated that Einstein's field equations of general relativity permit a metric, a description of space-time geometry, in which such a bubble exists and translates at faster than light velocity. The solution is mathematically consistent. It does not contain internal contradictions. It satisfies the Einstein field equations. This is why the concept receives serious academic attention rather than being dismissed as fantasy. It is a valid solution to the equations governing space-time curvature. But a valid mathematical solution is not the same thing as a physically realizable phenomenon. General relativity permits many space-time geometries that are mathematically consistent, but physically impossible. The Alcubierre metric requires a specific ingredient to function: exotic matter with negative energy density. This is not ordinary antimatter, which has positive energy and positive mass. Exotic matter would need to possess negative mass or negative energy, meaning it would gravitationally repel rather than attract. No such substance has ever been observed in nature. No experiment has ever produced it. No theoretical framework within the standard model of particle physics predicts its existence in macroscopic quantities. Quantum field theory permits fleeting negative energy densities in extremely constrained circumstances, such as the Casimir effect between closely spaced conducting plates, but the magnitudes involved are vanishingly small, and the conditions required bear no resemblance to what the Alcubierre drive demands. The quantity of exotic matter required is itself prohibitive. Early calculations by Alcubierre and subsequent analyses by physicists like Chris van den Broek and others estimated that the energy required to create and sustain a warp bubble would be on the order of the mass energy of an entire planet, or in some formulations the mass energy of the entire observable universe, converted entirely into exotic negative energy form. Later refinements reduced these estimates substantially, but even the most optimistic calculations still require quantities of exotic matter measured in solar masses. And these calculations assume that exotic matter exists at all, which it may not. There are deeper problems still. Physicists Stephen Hawking and others demonstrated that faster-than-light travel of any kind, including warp drives, creates potential violations of causality. If a ship can travel faster than light, even by warping space rather than moving through it, the mathematics of special relativity allows the construction of closed time-like curves. These are paths through space-time that loop back to their own starting point. In practical terms, this means time travel into the past becomes possible. Causality, the principle that causes must precede their effects, breaks down. Most physicists regard the preservation of causality as a fundamental requirement of any self-consistent physical theory. Any mechanism that violates causality is viewed with extreme skepticism, not merely as an engineering challenge, but as evidence that the mechanism cannot exist within a physically consistent universe. Hawking formalized this skepticism as the chronology protection conjecture, proposing that the laws of physics conspire to prevent the creation of closed time-like curves. If this conjecture is correct, and the weight of theoretical evidence supports it, then warp drives are not merely difficult to build, they are forbidden by the deep structure of physical law, for the same reason that perpetual motion machines are forbidden by thermodynamics. Additionally, analyses by physicists, including Jose Notario and others, have shown that the interior of a warp bubble is causally disconnected from the bubble wall. The crew inside the bubble cannot send signals to the bubble boundary. They cannot control the warp field. They cannot steer, accelerate, or decelerate the bubble from within. The bubble must be created and controlled entirely from outside, by some external mechanism that preconfigures the entire path of the warp field before the journey begins. This transforms the warp drive from a ship that its crew pilots into a rail that must be laid in advance by an external civilization with godlike engineering capabilities. Even in the most generous interpretation, this is not a solution to interstellar travel. It is a redescription of the problem in even more demanding terms. Traversable wormholes fare no better under rigorous scrutiny. The concept is based on solutions to Einstein's field equations discovered by physicists including Einstein himself, along with Nathan Rosen in 1935, and later elaborated by Kip Thorne and his collaborators in 1988. A wormhole is a theoretical tunnel or bridge through space-time, connecting two distant regions of the universe. If such a tunnel could be created and stabilized in an open configuration, a traveler could enter one mouth and emerge from the other, effectively bypassing the intervening distance entirely. The transit through the tunnel could in principle be brief, seconds or minutes, regardless of whether the two mouths are separated by light years or megaparsecs of normal space. The concept has been explored in hundreds of peer-reviewed papers. The mathematics, like the warp drive, is formally consistent within general relativity. Solutions to the Einstein field equations exist that describe stable wormhole geometries with traversable interiors. But once again, the solutions require exotic matter with negative energy density to hold the wormhole throat open against its own tendency to collapse. Without it, any wormhole that forms would collapse faster than light could traverse it. The throat of the wormhole would pinch shut in a time shorter than the light crossing time of the throat itself, making passage physically impossible. Stabilizing a wormhole large enough and long-lived enough for a spacecraft to transit would require enormous quantities of negative energy exotic matter, arranged in precise geometric configurations. The same substance that has never been observed, never been produced, and may not exist under the physical laws governing our universe. Wormholes also share the causality problem with warp drives. A traversable wormhole connecting two distant points in space can be converted into a time machine through straightforward relativistic manipulations involving relative motion of the wormhole mouths. This again creates closed time-like curves and violates causality. If Hawking's chronology protection conjecture holds, traversable wormholes are ruled out by the same deep principle that rules out warp drives. There is a pattern here that deserves explicit statement because it reveals something profound about the structure of physics itself. Every proposed mechanism for circumventing the speed of light barrier in a way that would make interstellar travel practical requires the same impossible ingredient: exotic matter, with negative energy density in macroscopic controllable quantities. Warp drives need it. Wormholes need it. Every other faster-than-light geometry that anyone has ever derived from the Einstein field equations needs it. This is not a coincidence. It is not bad luck. It is not a temporary limitation of human theoretical imagination. It is a consequence of the energy conditions in general relativity. The energy conditions are mathematical inequalities that constrain the relationship between energy density and pressure in any physically realistic distribution of matter and energy. They are the mathematical expression of the principle that gravity is attractive, that energy is positive, and that matter behaves in accordance with observed physical law. Every faster-than-light mechanism, whether warp drive, wormhole, or any other exotic geometry, violates one or more of these energy conditions. Violating the energy conditions requires exotic matter. Exotic matter has never been observed. The energy conditions may be fundamental constraints on what is physically possible in our universe, in the same way that the second law of thermodynamics constrains the direction of entropy. If so, faster-than-light travel of any kind is not merely beyond current technology, it is excluded by the architecture of reality. Some theorists have explored whether quantum gravity, the still undiscovered theory unifying general relativity with quantum mechanics, might offer loopholes. Perhaps at the Planck scale, where quantum effects dominate space-time structure, the energy conditions break down and exotic geometries become possible. Perhaps space-time is granular at the smallest scales, and that granularity permits shortcuts invisible to classical general relativity. Perhaps extra dimensions of space, curled up at scales too small to observe, provide pathways between distant points. These ideas are discussed in serious academic literature. They are not nonsense, but they are speculation built upon speculation. Quantum gravity does not yet exist as a complete, tested, experimentally verified theory. String theory, loop quantum gravity, causal set theory, and other candidate frameworks remain unverified by a single definitive experiment, despite decades of theoretical development. Not one prediction unique to any quantum gravity framework has been confirmed by observation. Building a case for interstellar travel on the hope that an unfinished, untested theory might someday permit what all current tested theories forbid is not physics, it is faith dressed in mathematical notation. And science does not advance by faith, it advances by evidence. The evidence, as of every experiment ever conducted and every observation ever recorded across more than a century of relativistic physics, is unanimous. The speed of light is the maximum velocity for causal influence in the universe. The energy required to approach it diverges without bound, and no mechanism for exceeding it has ever been observed, produced, or demonstrated to be physically consistent. Where does this leave us? What is actually possible within the laws of physics as they are understood and tested? The honest answer is sobering, but not entirely bleak. Small robotic probes, massing grams to perhaps a few kilograms at most, could potentially be accelerated to low fractions of the speed of light, using directed energy systems such as ground-based or space-based laser arrays, pushing against ultralight reflective sails. The Breakthrough Starshot Initiative, announced in 2016 with backing from the late physicist Stephen Hawking and investor Yuri Milner, proposed exactly this architecture. A fleet of gram-scale wafer probes accelerated to approximately 20% of light speed by a gigawatt-class laser array, reaching the Alpha Centauri system in roughly 20 years of flight time after a minutes-long acceleration phase near Earth. The fundamental physics is sound. 20% of light speed sits in the relatively gentle lower portion of the Lorentz curve, where energy requirements are very large by human standards, but have not yet entered the realm of the absurd. The Lorentz factor at 20% of light speed is only approximately 1.02. The relativistic corrections are small. The energy cost, while enormous, is at least conceivable for a sufficiently advanced civilization willing to invest in a dedicated laser infrastructure. The probes would be too small and too fast to decelerate at the destination, meaning they would flash through the Alpha Centauri system in a matter of hours, capturing what data they could during the brief, blazing flyby before sailing onward into the void forever. They would carry no crew, no life support, no return capability. They would be interstellar bullets fired once, never recovered, each one a message in a bottle thrown into an ocean that has no far shore. Even this modest proposal faces extraordinary challenges. The laser array required would need to maintain coherent beam focus across millions of kilometers during the minutes-long acceleration phase. The sail material must survive the intense radiation pressure of gigawatts of focused laser light without melting or deforming. The probes must carry communication systems capable of transmitting data back to Earth across 4.37 light-years, a feat requiring either surprisingly powerful miniaturized transmitters or extraordinarily sensitive receiver arrays at the home system. And the data returned would be limited to whatever a gram-scale probe can measure during a high-speed flyby lasting hours. No orbital insertion, no surface exploration, no sample return. A snapshot taken at extraordinary expense across interstellar distance. This represents the ceiling of what known physics permits for interstellar reach. Not crude exploration, not colonization, not the grand diaspora imagined by science fiction. A few grams of electronics flung past the nearest star at tremendous speed, returning a thin stream of data over years of light travel delay. Everything beyond this, every crude mission, every colony ship, every generation arc, every faster-than-light fantasy, collides with the same set of walls described across this entire story. The speed of light, the Lorentz factor, the energy divergence, the rocket equation, the deceleration trap, the interstellar medium, the absence of exotic matter. These are not separate problems with separate solutions. They are facets of a single geometric truth about the universe we inhabit. The light cone is the final and most absolute expression of this truth. In the space-time diagrams used by physicists to represent relativistic events, every object at every moment exists at the apex of a cone, whose sides are defined by the speed of light, extending forward and backward through time. Events inside the future light cone can potentially be reached or influenced. Events outside the future light cone cannot be reached by any means whatsoever. No signal, no projectile, No spacecraft, no influence of any kind can cross the boundary of the light cone. The cone expands outward as time passes, growing at the rate of 1 light year per year in every direction. But it expands only at the speed of light, never faster. No action taken by any object, no matter how energetic, how cleverly engineered, how technologically advanced, or how desperately motivated, can send any form of causal influence beyond its own light cone. This is not a limitation imposed on objects operating within space-time by some external rule. It is the definition of what space-time is. The light cone determines which events can be causally connected to which other events. It determines which regions of the universe are accessible from a given location, and which regions are forever and irrevocably beyond reach. For humanity, situated on a small rocky planet orbiting an unremarkable yellow dwarf star in the outer arm of a spiral galaxy containing 400 billion other stars, the light cone defines a sphere of possible influence that grows by exactly 1 light year per year. No more, no faster, not ever. In the nearly 300,000 years that anatomically modern humans have existed, our light cone has expanded to a sphere approximately 300,000 light years in radius. That encompasses a significant portion of the Milky Way, but it does not reach a single other galaxy. And even within that sphere, traveling to the edges would require time spans that exceed the entire history of our species, or energy expenditures that exceed the output of our star. The stars are not merely far away, they are far away in a specific mathematical sense that makes reaching them fundamentally different from every other distance humanity has ever crossed. Oceans can be sailed because water permits passage. Mountains can be climbed because gravity does not prevent ascent. The moon can be reached because orbital mechanics provides a pathway. Each previous frontier yielded to a combination of ingenuity and favorable physics. The interstellar frontier does not yield because the physics is not favorable. The physics is hostile, actively, mathematically, structurally hostile. The distances are denominated in light years. The energy costs are denominated in stellar outputs. The fuel requirements grow exponentially without bound. The interstellar medium shreds anything moving fast enough to make the distances survivable. And the speculative loopholes require substances that do not exist and may be forbidden by the same laws that create the barrier in the first place. There is a particular cruelty in this arrangement that deserves acknowledgement because it touches on something deeper than physics. The universe made us curious. Billions of years of evolution on a small planet shaped human brains to wonder about distant places, to feel the irresistible pull of unexplored territory, to look at a point of light shimmering in the sky and feel a visceral, almost physical desire to go there and see it up close. That yearning is not a flaw in human psychology. It is arguably the defining feature of our species. It drove our ancestors out of Africa and across every continent on Earth. It carried explorers across oceans they had no guarantee of surviving. It propelled us to the moon within a single decade of deciding to try. But the same universe that gave us the desire to reach the stars also wrote the equations that make reaching them impossible for any object of meaningful size traveling at any meaningful speed. We can see them. We can study them in extraordinary detail. We can analyze their light spectrum by spectrum and determine their chemical composition, their surface temperature, their rotational period, their age, and whether they host planetary systems with worlds that might harbor liquid water and atmospheres potentially capable of supporting life. We can do everything except go there. The night sky is a window, not a door, and the glass of that window is made of mathematics that does not break. Some will find this conclusion unbearable. The human instinct to reject limits is powerful, deeply rooted, and has served our species brilliantly for millennia. Every generation has been told that something is impossible, and every generation has proved the doubters wrong. Powered flight, the sound barrier, the moon, the genome. The pattern is so consistent, so deeply embedded in our narrative of progress, that rejecting any claim of impossibility feels like wisdom rather than denial. But we covered this distinction earlier. and it bears restating in its starkest form now that we have seen the full scope of the cage. Every celebrated breakthrough in human history operated within a permissive physical framework. The Wright brothers solved an engineering problem that the equations of aerodynamics always allowed. Jaeger broke a barrier that was aerodynamic, not fundamental. The Apollo program executed orbital mechanics that Newton could have computed 2 centuries earlier. In every case, the physics permitted the achievement from the start. Only the engineering was missing. Interstellar travel at relativistic speeds is fundamentally different in kind. The physics is not permissive. The equations do not leave room. The Lorentz factor does not plateau. The energy curve does not level off. The exotic matter does not materialize. The barrier is not ignorance waiting to be cured by knowledge. It is knowledge itself, the deepest and most thoroughly tested knowledge in all of physics, delivering a verdict that the human heart does not want to hear. And yet there is something that might be called grace in accepting that verdict. Understanding the cage does not diminish the wonder of what exists within it. Our solar system alone contains worlds of staggering variety. Moons with subsurface oceans, planets with atmospheres of methane and diamond rain, rings of ice orbiting gas giants larger than imagination. The Milky Way stretches above us every clear night, containing 400 billion stars, most of them hosting planets, many of those planets potentially harboring conditions suitable for life. We can study all of it. We can listen for signals. We can send our own. We can build telescopes that resolve the atmospheres of exoplanets and search for the chemical signatures of biology across dozens of light years. The universe denied us the ability to visit the stars in person. It did not deny us the ability to know them. Perhaps the deepest lesson embedded in the physics of interstellar travel is not about what we cannot do, but about what kind of universe we live in. We inhabit a cosmos of extraordinary scale and beauty that is fundamentally structured around isolation. The distances between stars are not accidental. They are consequences of how gravity, nuclear physics, and stellar evolution distribute matter across galactic space. The speed of light is not an arbitrary limit. It is the rate at which causality itself propagates, the fundamental clock speed of reality. The energy costs of relativistic travel are not design oversights in an otherwise navigable universe. They are direct expressions of the relationship between mass, energy, and space-time geometry. Everything fits together. The universe is not broken. It is not poorly designed. It is not waiting for someone clever enough to find the back door. It is a structure of immense internal consistency, and that consistency includes the fact that stars are visible but unreachable. Humanity has always defined itself by its willingness to push against boundaries. That impulse will not end here. We will continue to build faster probes and more sensitive telescopes. We will continue to study the interstellar medium and refine our understanding of relativistic physics. We may someday launch gram-scale probes toward the nearest stars and receive thin streams of data from alien solar systems for the first time. These achievements would be genuine and magnificent, and they would unfold entirely within the constraints described in this story. The laws of physics are not enemies to be defeated. They are the language in which reality is written. Learning to read that language honestly, without flinching from what it says, is not surrender. It is the highest expression of the same curiosity that made us look at the stars in the first place. The stars burn tonight as they have burned for billions of years. Their light crosses the void and reaches our eyes and fills us with wonder. That light is real. That wonder is real. The distances between us and those ancient fires are also real, and they are governed by equations that do not yield to hope, to funding, to genius, or to time. We are a species that can see across the universe, but may never cross even the smallest gap between neighboring stars. That is not a tragedy. That is the universe, honest and complete, telling us exactly what it is. And what it is, even confined to the tiny fraction we can touch, is more than enough to fill every lifetime our species will ever live with discovery, with awe, and with the irreplaceable privilege of having understood, even briefly, the nature of the cage we call home.
They tell you the
Mornings. Right. Right.
I'm just trying to tell you, babe. You didn't even say take place. One, two. That's literally scary to me. You didn't even see it take place, did you? Right? You see here, yes, that movement, yeah. One, two. That's literally scary to me. Right? Because there was one time, there was this guy, and it looked like something was going to die. That's scary to me. Single Mister. That's literally scary.
Got my own symptoms of.
Because there was one time, right? There was this guy, and it looked like something
I'm
was
just
going
not.
to die. That's scary to me. Single Mister. Yeah, it's really scary to me. You don't even know me, that's what I'm trying to tell you. You know what I mean? Like, you don't even know me, though. So I'm going to tell you that, yeah. That's my wife. I meant like you. You're one of the judgmentalists, aren't you? Yeah. I've heard about them. Apparently, what they do is they judge. You don't even know me, so I just judge my life.